Hi, this is Jim, W6LG for Ham Radio Basics. Welcome to my radio room classroom here on Wolf Mountain. These 10 videos are a review of all of the 462 questions that make up the general license question pool. The idea behind the videos is a way to prepare for the exam. I'm going to be reading the question and then the correct answer, and when I can, I'll provide a brief explanation as to why that happens to be the correct answer. So here we go. This is part 8, 9, G9A01. Which of the following factors determines the characteristic impedance, we're talking about AC, of a parallel conductor antenna feed line? Could be ladder line, window line. It is the distance and the size of the conductors, and that just makes sense. So the further apart they are, the higher the impedance. So it's A, the distance between the centers of the conductors and the radius of the conductors, size of the conductors, and how far apart they are. G9A02. What are the typical characteristic impedances of coax cables used for antenna feed lines in amateur stations? The obvious answer here is most coax cables are 50 ohms, so B is 50 and 75. G9A03. What is the characteristic impedance of a flat ribbon TV type twin lead? Well, TV twin lead, I think we all know, is 300 ohms, so it's D. G9A04. What might cause reflected power at the point where the feed line connects to the antenna? The answer that makes sense here is the feed line has one impedance and the antenna has another. There's a mismatch. Let's go through the other ones. Operating an antenna at its resonant frequency. The resonant frequency of the antenna, that's where there's no reactance, could be any impedance. That one has a possibility. A difference between the feed line impedance and the antenna. Oh, that is the right answer. Using more transmitted power? No, has nothing to do with that. Feeding the antenna with an unbalanced feed line. That'd be saying feeding it with coax. No, that doesn't cause reflected power. It's C, a difference between the feed line impedance and the antenna impedance. So there's a mismatch in impedances. Easily solved, though. Many different ways. G9A05. How does the attenuation of coax cable change as the frequency of the signal it's carrying increases? Well, as you go up in frequency, the loss increases. So it's B, attenuation increases. The higher the frequency, the more the loss. G9A06. In what units is RF feed line loss usually expressed? Well, it's decibels. And the typical length that we use is dB per 100 feet. So, for example, if you're looking at a table with feed line losses, for most times it's going to have a column that's labeled per 100 feet. So I have seen it for 1,000 feet, by the way. G9A07. What must be done to prevent standing waves on an antenna feed line? Okay, so when they're talking about standing waves, they're talking about SWR. So what can be done to prevent, let's say, an SWR? The antenna feed point impedance must be matched to the characteristic impedance of the feed line. So characteristic impedance is just another way of saying the impedance of the feed line. So the feed line is 50 ohms. It's best if the antenna has a 50 ohm impedance. If the coax is 75 ohms, the antenna is best if it has a 75 ohm impedance. And there are ways to get there. So the answer is D. G9A08, if the SWR in a feedline is 5:1, and a matching network at the transmitter end of the feedline is adjusted to a 1:1 SWR, what is the resulting SWR in the feedline? Well, the SWR in the feedline is the SWR in the feedline. It's 5:1. So it's B. It doesn't change. What they're saying here is you're using an antenna tuner at the transmitter to get a 1:1 SWR. How does that change the feedline? Well, it doesn't. It's just a matching device. A9A09. What standing wave ratio will result when connecting a 50 ohm feedline to a non-reactive load having a 200 ohm impedance? SWR is expressed in some number to 1, so it's 4:1. You may have heard the expression 4:1, 5:1, 10:1. It's always going to be something to 1, so this is a ratio of 4:1. G9A10. What standing wave ratio will result when connecting a 50 ohm feedline to a non-reactive having a 10 ohm impedance? So here we've got a 5:1. And again, it's always going to be some number to 1. It's D. G9A11. What standing wave ratio will result when connecting a 50 ohm feedline to a non-reactive 50 ohm? Well, that's a good thing to do. So that's 50 ohms to 50 ohms. That's a 1:1. G9A12. What standing wave ratio will result when connecting a 50 ohm feedline to a non-reactive 25 ohm impedance? Again, it's always going to be some number to 1. So the ratio here is 2:1. The answer is A, 2:1. G9A13. What standing wave ratio will result when connecting a 50 ohm line to an antenna that has a purely 300 ohm feed point impedance? Okay, so there's 6:1. That's the ratio. Again, it's always some number to 1. G9A14. What is the interaction between high standing wave ratio and transmission line loss? What is the interaction between high SWR and transmission line losses? Well, the higher the SWR, the greater the line loss. So their answer is if a transmission line is lossy, high SWR will increase the loss. That's very true. There's a warning here, though. Think of it this way. The losses increase because the transmitted signal isn't radiated the first time it gets to the antenna. It's reflected back down the feed line, back to the transmitter, back out. So each time it makes this round trip, it may take several times for it to be radiated. Each time it goes up and down the coax, there's more transmission line loss. However, if you're looking at the SWR from the transmitter, as the feed line losses increase, the SWR looks lower. G9A15. What is the effect of transmission line loss on SWR measured? Oh, this is the thing I just said. What is the effect of transmission line loss on SWR measured at the input to the line? If you think about, let's say, a really lossy line, let's say 50% of the power that goes into the coax is lost. Well, what's reflected is also lost. So the SWR looks better than it really is because that reflected power is lost in the coax. So instead of there being, let's say there's 100 watts going out and 10 watts being reflected at the feed point, instead of it being 10 watts at the transmitter, maybe it's 5 watts because of feed line losses. What is one disadvantage of directly feeding random wire HF antennas? They say you may experience RF burns when touching metal objects in your station. Vertical signal. Well, none of the ones make any sense, but that's very true. G9B03. What happens to the feed point impedance of a ground plane antenna when its radials are changed from horizontal to sloping downward. The impedance increases. Unless you've done this, the impedance increases. G9B04, what is the radiation pattern of a dipole in free space in the plane of the conductor? What is the radiation pattern of a dipole in free space in the plane of the conductor? It's figure 8 at right angles to the antenna. Again, you'd have to have some experience with modeling antennas, but radiation pattern of dipole antenna in free space, plane of the conductor. That's just a plain confusing question. Their answer is it is a figure 8 at right angles to the antenna. G9B05. How does the height affect the horizontal azimuth pattern of a horizontal dipole? Well, if the antenna is less than half a wavelength, the azimuthal pattern, that's easy for me to say, is almost omnidirectional. How does the antenna height affect the horizontal radiating pattern of a horizontal dipole at HF? Okay, this is one you're just going to have to go with your answer. It's if the antenna is less than half wavelength high, the pattern is almost omnidirectional. That's their answer. I strongly disagree with that. It depends. And it depends on a lot of things. It depends on the topography, for one thing. So if that dipole, in fact, here, if that dipole is half a wavelength high, its effective height for me on the side of a mountain is very different, and it's not omnidirectional. That answer needs to indicate flat ground and a bunch of other things. G9B06, where should the radio wires of a ground-mounted vertical antenna system be placed? Okay, G9B06, where should the radial wires of a ground-mounted vertical be placed? Okay, the vertical is mounted on the ground. Their answer is on the surface of the earth or buried a few inches below. Actually, it works better if they're a few inches above the ground. If I were to mount a vertical as they describe, I would have the radials off the ground a bit because it just flat works better. There are less losses. Their answer, however, is on the surface or buried. When you bury the radials, they become very ineffective, and you have to have lots and lots and lots of radials. If they're a few inches above the earth, 4 radials will work great. Put them on the ground or below the ground, you're going to need bunches. So I don't like their answer again. And I'll take this up with the VEC guys. But again, you've got to give the answer that they say is the right answer. If they say it's blue, it's blue. G9B07. How does the feed point impedance of a half-wave dipole antenna change as the height is lowered below a quarter wavelength above ground? The closer to the ground it gets, the lower the impedance becomes. And they have A increases, no. B decreases, yes. C is just flat untrue. Unaffected, not true. G9B08. How does the feed point impedance of a half-wave dipole change as the feed point is moved from the center towards the ends? Well, that's a good question. As you move away from the center, the impedance and the voltage increases. So if you feed it at the very end, it's technically and infinite impedance. So as you move away from the center, the impedance increases. G9B09, which of the following is an advantage of a horizontally polarized as compared to a vertically polarized HF antenna? Let's see, they have lower ground reflection losses. Well, that's true because I talked about dipoles and having or verticals and having the radials on the ground. There is not much in the way of ground reflection losses on a dipole. The others, another answer that might be possible, but it's not on there, is there's less noise. G9B10, what is the approximate length for a half-wave dipole cut for 14250? Well, I know the length of this really well because I have Yagi antennas for 20 meters. In prior videos, I've talked about a way to compute a quarter wavelength, and the answer I use is 1, 2, 3, 4, meaning that one side of the dipole is 234 divided by the frequency in megahertz. So 1, 2, 3, 4. One side is 234 divided by 14250. If you do that math, that answer for one side is 16 feet. We're talking about both sides in the question, so it's D, 32 feet. G9B11, what is the approximate length for a half-wave dipole cut for 3.550 megahertz? Well, the answer there is 131 feet. And again, you can do the formula. You can also memorize. It's a good thing to memorize those lengths. 20 meters is about 32 feet. 40 meters is about double that. In fact, if you remember one, you can probably remember the others, except maybe for, well, Workman's in 15. But if 20 meters is 32 feet, roughly, 40 meters, roughly double that. So 64 feet, let's say 64 feet. Double that to get to 80 meters. That number then comes out to 128. Depending on what you're putting up, 131 is a good answer too. It changes a bit depending on other factors. G9B12, what is the approximate length for a quarter wave vertical? Now we're talking about quarter wave this time, cut for 28.5. So that's 10 meters. Even though I hate to say it, think of CB whip. CB whip is about 8 feet long. If you put a mobile antenna on a car, the whip needs to be about 8 feet long. So the answer is 8 feet. And again, if we're looking at 20 meters, a quarter wave on 20 meters is 16 feet. Going to 10 meters would be half that much, 8 feet. G9C01, which of the following would increase the bandwidth of a Yagi antenna? Yeah, larger diameter elements will, and that's true of really pretty much any antenna. Closer spacing, no. Loading coils, no. Taper elements, no. They'd all do the opposite effect. G9C02, what is the approximate length of a driven element on a Yagi antenna? Well, typically it's a half a wavelength. It's a dipole, so it's a half wave dipole. What is the approximate length of the driven element of a Yagi antenna? The question that I come up with on this one is, are we talking about electrical length, physical length? But the answer in all cases is going to be half a wavelength. G9C03, which statement about a 3-element Yagi, I rephrase that, which statement about a 3-element single band Yagi is true? In a Yagi antenna, the longest element is the reflector. The driven element is in a 3-element Yagi is in the middle. the shortest element, the one at the shortest end, at the direction it's pointing in, it's called the director, and that's the shortest element B. G9C04. Which statement about a 3-element Yagi, reading it ahead, which statement about a 3-element single-band Yagi is true? The reflector is normally the longest element. So a 3-element Yagi, the reflector is the longest, the director is the shortest, driven element is typically in the middle. There are exceptions to that rule. G9C05, how does increasing the boom length and adding directors affect Yagi antennas? Well, it increases the gain. The bigger the antenna, the better the gain. More elements, generally speaking. That doesn't mean you can take a 12-foot, let's say a 20-meter Yagi with a 20-foot boom, which is about right. Optimal length for a 3-element Yagi on 20 is a 24-foot boom. So let's say you decided, all right, I got a 24-foot boom. Let's put 10 elements for 20 meters on there. It's not going to improve the performance. Lengthen the boom and add elements? Yes. G9C06, what configuration of loops of 2-element quad antennas must be used for the antenna to operate as a beam antenna, assuming one of the elements is used as the reflector? Wow, confusing parameters for that one. 2-element quad typically has a reflector and a driven element. On Yagis and quads, just as a rule of thumb, yes, there are exceptions. Just as a rule of thumb, between 3 and 5% is the variation in the length of the elements. There are exceptions. On a 2-element quad, the reflector must be, it says the reflector must be approximately 5% longer than the driven element. Again, I don't agree with the answer. It doesn't have to be 5% longer. Depends on the spacing. Could be a larger number, but as a rule of thumb, 5% is correct. G9C07, what does front-to-back ratio mean in a Yagi antenna? Just pretty much what it says. If you compare the signal from the front of the antenna to the rear of the antenna, what is the ratio? And it's usually expressed in dB. The front-to-back, for example, on a Yagi might have a front-to-back ratio of 20 dB. 20 dB, as we've discussed before, is a 1 and 2 zeros, so there's 100 times difference between the front of the antenna and the back of the antenna. Their answer is C, the power radiated in the major direction lobe compared to the power radiated in exactly the opposite direction. So that's generally in the same line. So it's the front lobe turn around 180 degrees compared to the rear of the antenna. G9C08, what is meant by the main lobe? That's the lobe at the front of the antenna. And so it's D, the direction of maximum radiated field strength of the antenna. G9C09, how does the gain of two 3-element horizontally polarized Yagis spaced half a wavelength apart compared to a single 3-element Yagi? Well, I'm doing something like this at home, and there are exceptions to this, but in round numbers, if you double the size of the antenna system, in this case we're going from 1 Yagi to 2, there's doubling is approximately 3 dB gain, and that's what they're saying, 3 dB. G9C10, which of the following is a Yagi antenna design variable that could be used to adjust, let me read this again. G9C10, which of the following is a Yagi antenna design variable that could be adjusted to optimize forward gain, front to back, or SWR bandwidth? Physical length of the boom. Physical length of the boom. Okay. Number of elements, spacing on the elements, all those things can make changes. So the answer is D. G9C11. What is the purpose of a gamma match? Well, it's to match the impedance. So Aayegi tends to have a lower than 50 ohm impedance, 25, 30 ohms. So the purpose is to match the relatively low feed point impedance to 50 ohms. G9C12. Which of the following is an advantage of using a gamma match for impedance matching of a Yagi antenna to 50 ohm coax? How many prepositions are there in that sentence? Which of the following? Of, for, of, to. Jeez. Their answer is it does not require the elements be insulated from the boom. Okay. On a gamma match, the elements do not need to be insulated. The gamma match, it's attached to the boom and it's right at 0 in terms of voltages. Why is that an advantage? If you're building an antenna with your own parts and pieces, it's really hard to find a way to insulate the elements from the boom. So by using a gamma match, you can use hose U-bolts and attach the elements right to the boom and then still get it to match. It's almost magic. G9C13. Approximately how long is each side of a driven element on a quad? Now this one's a bit tricky. So we're talking about each side of the quad. A quad loop is one wavelength, but they're only taking one side, so typically it'd be 1/4 wavelength. G9C14. How does the forward gain of a 2-element quad compare to the forward gain of a 3-element Yagi? They're about the same, and that's the answer they have. Somewhere in the neighborhood of 6 dB on a good day. G9C15. Approximately how long is each side of the reflector of a quad antenna? Okay, the reflector is slightly longer than the driven element. Each side is 1/4 wavelength plus 3 to 5%. So their answer is slightly more. Here's what's misleading. G9C15. How? I'm going to read this just as it's written, if I can. G9C15. Approximately how long is each side of the reflector element of a quad? And their answer is slightly more than 1/4 wavelength. I would like if it said slightly longer. G9C16. How does the gain of a 2-element delta loop compare to the gain of a 2-element quad? They're about the same, maybe a hair lower, but they're about the same. G9C17. Approximately how long is each leg of a symmetrical delta loop? Each leg, it's a triangle, so each leg is about 1/3. B. G9C18. What happens when the feed point impedance of a quad antenna of any shape is moved from the midpoint of the top or horizontal or either side? It changes the polarization depending on where you break the wire and insert the feed line. Changes the polarization of the element. So if you feed it, let's say in the bottom leg of that quad, it's horizontal. If you feed it on the vertical side, it's going to be vertically polarized. And that's our answer A. The polarization of the radiated signal changes from horizontal to vertical. G9C19. How does antenna gain stated in dBi isotropic compare to the gain dBd dipole for the same antenna? dBi is 2.15, 2.15 dB greater. So their answer is B. think of this one as the model free space, the dipole, a more realistic look in a given situation. G9C20. What is meant by the terms dBi and dBd when referring to antenna gain? Isotropic, and dipole. So it's A. dBi refers to isotropic antenna. dBd refers to a dipole antenna. Isotropic radiator. G9D01. What does the term NVIS mean? Near vertical incident skywave. Somebody made this one up, but that's what they're called. NVIS is often the way it's said. So it's near vertical incident skywave. It's an antenna that's like a dipole antenna that is placed close to the ground. It tends to radiate upwards. Cloud warmer. G9D02. Which of the following is an advantage of an NVIS antenna? High vertical angle radiation for working stations within the radius of a few hundred kilometers. Interesting that everything else on this exam has been in feet, and in this one, a few hundred kilometers. We've used NVIS during emergency situations, so you string up a 40-meter dipole, you put it a few feet off the ground, and you can talk to the main station, the main emergency station that maybe is just a few miles away. By that I mean maybe 50 miles. G9D03. At what height above ground is an NVIS antenna typically installed? And the right answer here is a tenth of a wavelength to a quarter wavelength, typically really close to the ground. G9D04. What is the primary purpose of antenna traps? They allow the antenna to be used on more than one frequency. They're sort of like switches. They turn off and on the rest of or connect the rest of the elements. So you can literally place a trap down an element and get it to resonate on a much higher frequency, much shorter wavelength. So it says to permit multi-band operation. Typical tri-band antenna, tri-band 3-element beam, has traps. G9D05. What is an advantage of vertical stacking of horizontally polarized Yagis? What is an advantage of vertically stacking horizontally polarized Yagis? What happens is they end up with more gain, and gain, almost by definition, is a narrowing of the main lobe. So it's D. It narrows the main lobe and results in greater gain. G9D06. Which of the following is an advantage of a log periodic antenna? Very interesting antenna. They cover huge frequency ranges, and if you've seen one, if you haven't, take a look online. They have very short elements at the beginning and very long elements at the end, and cover huge. For example, can cover from 3 to 30 megahertz. G9D07. Which of the following describes a log periodic antenna? Well, it's got really huge number of elements typically, and they vary from being very short to very long. So it's a length and spacing of the elements increases logarithmically from one end of the boom to the other. So the spacing changes, as does the length of those elements. G9D08. Why is a Beverage antenna not used for transmitting? They have huge losses. They're great for receiving. Usually they're on 160 meters. They have huge losses, but then along with that, there's a greater reduction in noise. So they tend to be pretty quiet and allow the guy to hear stations that he maybe can't hear with another antenna. G9D09. Which of the following is an application for a Beverage antenna? It's B, as I described. It's a receiving antenna for low HF bands like 160. G9D10. Which of the following describes a Beverage antenna? I don't know why there's 3 questions on here, but it is a very long and low directional antenna. Pattern tends to be in the direction of the wire. As is true with most antennas, the longer they get, the more the pattern goes towards the direction of the wire. G9D11, which of the following is a disadvantage of multiband antennas? Okay, their answer is